Okay. Alright, let's start. So, before I start talking about quantum mechanics, I want to talk about classical mechanics. The reason is, to understand quantum, you have to understand classical, and that should sound pretty obvious at this point. So, one of the most basic things we can talk about in physics is, or at least in mathematical physics, is something called the the Lagrange's equation of motion, or the Lagrange's equation. So it's pretty mathematical and it's pretty straightforward. Okay, so let's start with this theorem. Okay, so what Lagrange is trying to study in the big picture is, if you have, suppose, let me color this actually. If you have a coordinate plane, R2, right? This is a coordinate plane R2, as you can pretty much see. And you have this, right? Well, in this case, it's pretty obvious. The minimal distance from, let's suppose that this one is x1 here, and suppose this one is x2 here, right? So the minimum distance that one can travel is this, right? I mean, this much is pretty obvious. A straight path is much faster than a curved path, right? It's much faster than this path, or it's also much faster than this path, right? I mean, this is pretty much the straight way to go to the point, right? I mean, a straight way is much faster, but suppose we don't know where the points are. Like, the points are very off, like it has a huge distance between them. Then it becomes obvious that in the whole space, it becomes less obvious that what is the most direct path. And Lagrange mechanics facilitates the study of minimal distances, and we call this the principle of stationary action. So, to understand the principles of stationary action, we have to understand the mathematics of what this thing comes from. So as you might have heard, there's something called the Lagrange's equation of motions, which I'm going to derive for you, actually. And this starts by a theorem. A simple theorem. Very simple theorem, actually. Theorem. I want to know my theorems like this. So, theorem. What my theorem states is that if the function f of t, the function x of t is a stationary value. A stationary value means 0. In physics, or in anything, nothing is stationary if it's not 0. And that also, obviously, stationary value gives a critical point in mathematics, which gives a local maximum, minimum, or saddle point. So, right? So it gives us of S. So here, S means a stationary action. Then the following equation is satisfied, as surprising as it sounds. The derivative in respect to time t times the partial derivative of the Lagrangian operator of partial x naught is equals to the partial derivative of the Lagrangian operator of partial x naught. So one thing you have to realize is that if we have an x naught here, right? In physics, when we use the dot notation, it means it's a time derivative, which means that you can think of it as something like this. dx naught as a function of time divided by dt. As an ordinary derivative. It's much simpler to think it this way. So when we look at this, and this is something called the Euler-Lagrange equation. And in the Euler-Lagrange equation, it is well understood that not well understood. The boundary conditions are well understood in a certain way. So what I mean is, here, important thing is that boundary conditions of this equation, is well understood. Which means we have a Dirichlet boundary condition, since it's a homogeneous, you have a Dirichlet boundary condition in this case because it's homogeneous and it gives the same values. Dirichlet it's a Dirichlet condition. From basic PDEs, you should know what Dirichlet condition is actually. x1. So at initial time, we get the first iterated function, which is x1, and the second, and at xt2, the second position of this, actually this is one, xt1, we get the first iterated function, and xt2, we get x2 as the second iterated function. So our job is to prove this theorem. Just like mathematics, we prove everything. So the best way to understand this actually is through something called a Taylor series, and I'm sure you've heard what the Taylor series is, but okay, so let's prove this. So a simple proof of this is, let us say that f of x, where x in this case is the position vector, is equals to some locus set of points of x1 to xn, where x1 to xn is a set of points that defines f of x, with a minimum with a minimum x naught, which is characterized by the fact that if we move away a small distance eta, and note that eta here is not a constant actually. In any direction, in any direction. So in any direction means you can move north, east, west, south, whatever you want, north, east, south, east, doesn't matter, any direction. Then the action of f, which we here denote by the small delta, lowercase delta f, and f vanishes. So here we're saying that if f of x is equals to fx1 to fxn, so we have a set of position vectors x1 to xn with minimum x naught. So we have a minimal point at x naught that is a stationary actually, which is characterized by the fact that if we move away any distance, right, any direction in the action of f, meaning in the action of f, then f vanishes. So since we can say that, we can describe this function as in terms of Taylor expansion, and the Taylor expansion looks something like this. Oopsie. Okay, the Taylor expansion looks something like this. F of x naught plus eta, right? So eta here is a function of time. Again, I repeat. Can be expressed as something like f of x naught, right? So the initial frame, which is the minimum of this case, in this case, mathematically, plus the sum of I equals 1 to n. So it's a partial sum at that. It's a Taylor expansion, but it's a partial Taylor expansion, actually, in this case, plus partial f partial xi of x naught. So we have a directional gradient plus times eta sub I plus O sub eta sub I, where O here is the big O notation and it stands for the Bachmann-Landau notations, or it's the infinite asymptotics. So in this case, we say partial f partial x, so we assume something. We say that first note that partial f partial x is ith dimensional, along with eta. Okay, and for this particular case, we're going to assume that partial f of partial xi is equals to 0 for all I equals to 1 to n. Okay, and n is a positive integer in this case. So we're gonna say, let me scroll this down. How do I scroll? So I'm gonna say that that going to say that the path of least action x x of t plus a-s of t. So we're going to say that, wait, that the path of least action is x of t plus some a-s of t, so that we can have the Dirichlet, so that we can satisfy the Dirichlet boundary condition. Dirichlet boundary conditions, which are saying that a-s of ti equals a-s of tf has to be equals to 0. So, given that, so let us try to prove this mathematically. So let ti be this, let t be defined on this continuous interval, where t is actually Lipschitz continuous, and so in other words, t is defined on ti to tf, and it's bounded / Lipschitz continuous. I'm sure you've heard about what Lipschitz continuous means in analysis. Oopsie. So let us take the integral of the action. So let us say the following. Let us say that the action S, when I'm going to use a different notation here. In the previous notation, I used delta to define the action in F. I principally like to use S as a notation. So delta, you'll see in British textbooks that they use delta to describe actions, but in American textbooks, they usually use S. So it's a matter of preference. It doesn't really matter actually at this point. So x of t plus a-s of t, right? So we're taking the action of the least action, right? And so technically hypothetically, when you do this experiment, if you take the integral of a bounded function of ti to tf, which is a Dirichlet condition, if you take the integral of that function, you're supposed to get a 0. Okay, so the main point here is we have to prove that this integral, or this action of this Taylor expansion, is going to give us 0, which can be a pain in the butt, actually. So let us suppose that the action is equals to, obviously, the integral of the Lagrangian. The Lagrangian is an operator. It's a linear operator at that, so it's a very nice operator. Times x of t plus a-s of t, right? So we took the integral of the least action, right? Times, because it's a partial Taylor expansion, we take the derivatives of that respective to it. So we get that we take the derivative respective to time, so we're going to put a just dot over this. X prime of t plus a prime of t dt. Okay? So we took the integral of that. Okay, good. Okay, now, we expand this term. We use the Taylor expansion to expand x of t plus a-s of t, right? And x prime of t plus a prime of t. And we get the following. Now we expand. So, expanding. Right? We expand. So we got this is equals to x of t, right, initial, plus x prime of t. Again, take the derivative. Nothing surprising over here. Take the directional derivative plus we take the Lagrangian. We take the derivative of the Lagrangian with respect to t. Times the eta function here. Right? I mean, we're literally just expanding this formulation over here. So it's not much of a surprise here. Plus eta of t plus we're gonna take another derivative, and we're gonna get is the partial derivative of the Lagrangian operator times x prime of t times eta prime of t, and so on. So O of eta squared, eta prime squared. Okay. So as you know, if these values x prime of t is going to be very minimal, and plus, because we said that x naught is a minimum, so it's going to be at like the boundary point, so it's going to be zeros. It's basically equivalent to zero, or if it's not zero, we will not really care about it because the values are going to be so minimal that it's not going to be worth looking at. So because the integral of the action has to be zero for these cases, because that's what we're trying to prove. I mean, if we took the minimal distance, then the integral between the initial and the final time is going to be zero in physics by the very basic law of physics. So 0 is going to be equal to the action of f, which is the action here, of this function here, the Lagrangian, the blah blah whatever there, s, and this, I'm going to say that this is equals to integral ti to tf of the partial derivative of the Lagrangian x of t times eta of t plus the partial derivative of the Lagrangian at the partial x prime of t plus eta prime of t, right, dt. Okay? So to integrate this, we have to use integration by parts. What a surprise! We have to use integration by parts. It's really not a surprise. So let's use integration by parts. So let us say here, u here is going to be the partial derivative of the Lagrangian of partial x prime of t, such that du is going to be equals to is the derivative of respective to time t times the partial derivative of the Lagrangian of partial x prime of t. Okay? And we get dv is equals to eta prime of t, and v is equals to eta of t. Okay? Such that, and yeah, obviously using the integration by parts, right? We integration by parts. So how do you write that? IBP. Integration by parts, IBP. We get that the partial derivative of the Lagrangian of partial x prime of t times eta sub t tf ti minus the derivative with respect to time t of the integral ti to tf partial derivative of the Lagrangian of partial derivative of x of t eta sub t dt. Okay? And you can try the calculations yourself, because plugging in eta t sub f minus eta t sub I, that's just going to disappear. So factoring eta sub t out and doing all the operations, you can find out that the partial derivative of the Lagrangian of partial x of t minus the derivative respective to time of partial derivative of the Lagrangian of partial x prime of t times eta sub t is going to be equal to 0 for ti t to tf. And therefore, right, so therefore, let's read it. Okay, so therefore, the derivative in respect to time t, or the partial derivative of partial x naught, right, minus partial derivative of the Lagrangian of partial x naught is equals to 0. Hence, the Euler-Lagrange equations are satisfied for bounded time intervals in the Dirichlet conditions. Okay? So now, do this problem by yourself, and let's talk about this in the future. I will send you the problem by email. Bye.